All right, in this, our last podcast of Unit 2, we're going to be talking about electromagnetic radiation, what it is, mostly on page 20, then how to do some calculations for it on page 21. As we get started, the simplest way to think of this electromagnetic radiation is just a form of light. Normally, we just think of light as the visible portion of this spectrum, the colors that we can see that light up the room, but there are lots of other types of electromagnetic radiation. All it is, the formal definition, is a form of energy that exhibits wave-like behavior as it travels through space. And the only difference between the visible light that we can see and the x-rays that they use to tell where your bone is broken if you broke something, or the microwaves that you use to heat up food, radio waves to listen to music, is the wavelength, frequency, and energy. They're all just waves, but the properties of those waves are just a little bit different. And that makes a big difference when it comes to how powerful they are and how dangerous they are. So let's talk about this relationship real quick. Like you see already written on your page, these short wavelengths, meaning there's a short distance between the waves, are the ones that have higher energy. If you were trying to make this wave with a string maybe attached to a doorknob or something, you'd have to shake it pretty fast, pretty hard, put a lot of energy into making these waves, make sure that they're as close together as possible with that shortest possible wavelength. On the other hand, these waves over here at this end of our spectrum are much longer waves. They're much farther apart, and because of that, they wouldn't require as much energy in order to form a wave like this with a string tied to something. The other term that you see here is frequency. Frequency is kind of like wavelengths, but it's also kind of the opposite. Kind of imagine a person standing on the shore of a beach, and these might be ocean waves coming at them. The longer our wavelength is, then the less frequency, the lower the frequency is that someone is going to be getting hit by this wave. So on this side of our spectrum with these long wavelengths, they have a long time in between the waves, which means that they have a very infrequent wave. They might get hit, knocked over by a wave, but they have enough time to stand up and brace themselves before the next wave. That is not the case on the other side of our spectrum. If we were standing here on the shore and these waves are coming at us off of the ocean, then we're going to be getting hit one after another, after another, after another. This really short wavelength gives us a very high frequency of waves, which tends to be higher in energy as well. So you'll notice on either side of the spectrum, our frequency and our energy are directly related, meaning that they go the same direction. High frequency, high energy, low frequency, low energy. And then our wavelength is the opposite. It's inversely related to these other two. So the smaller the energy and the smaller the frequency, the bigger our wavelength is. And you're going to need to be able to compare these properties with these different types of radiation in order to be able to say that microwaves are longer wavelengths than X-rays. And you're also going to need to be able to do that with our colors of visible light. So it might be worth writing down our Roy G. Biv. It might seem like it's going backwards here with the way that it's drawn on my paper, but please make sure you write it down this way instead of opposite, because that's just the way this spectrum has been set up to go in this direction. We could have flipped it around to make these colors go in kind of your more normal rainbow order. They are still in the same order, it's just kind of the opposite direction. So red has longer wavelength than violet, and it's important that we get that kind of written out in the correct order for that. So next kind of big idea here is our emission spectrum. We're going to be looking at specific lines of color produced when the electrons in an atom get excited. And so this is where we already have written for you our ground state and excited state definitions, and we're going to come back to these again in a minute. Ground state is just where our electrons are supposed to be. We've been writing ground state electron configurations, and the word ground state just seemed like extra. You kind of ignored it the whole time. Well, now we're going to have our electrons not where they're supposed to be. They're going to be getting excited and jumping to higher energy levels. So that's why you probably saw that word a lot before. It just meant everything is normal. Well, now our atoms aren't going to be normal. We're going to be seeing some spectrums come out of these flame tests, of these elements, and it's not going to be a continuous spectrum like what we saw up above with our electromagnetic spectrum, where it's a nice smooth transition from red to orange, yellow, green, blue, violet, and every color in between. All the spaces are filled with no gaps. That's what the continuous spectrum looks like. That's not what we're going to be seeing as our emission spectrum. As our line spectrum, we only see separate lines of color there. It still can cover all of the different colors, but there's gaps in between. And that's because, as we've talked about before, there are gaps in the atom where our electrons aren't allowed to be. There's only certain specific energy levels the electrons are allowed to be on, and these lines are showing us what levels those are in the atom, because these colors of light come from the electrons moving in between those levels. And that's what we're going to get to next. But unfortunately, this next section kind of broke across a page because of that weird alignment issue we had. So make sure that you get the top of page 21 filled in as we're going through these notes here. And we have this little space where you could have written the excited and ground state definitions again, and you don't have to write the same thing over again. That's all I've written for ground state, is the lowest energy state. But the excited state, like we said before, is a higher energy. That's where our electrons are going to be going up to. It's always going to be higher than the ground state. So you might make a quick note either up top where we had already written the excited state information, or you could kind of cover up that weird diagram that for whatever reason got smushed into those words here. We don't really need that diagram. So you can white it out, cover it up, write this here if you want, or just leave it. I just want to make sure to have those definitions here as we start to talk about the electrons and see these move in our atom. So each of those lines in our emission spectrum, our line spectrum, is the photon of a very specific energy being released by the atom. And that energy for that photon is equal to the difference between the ground and excited state for the electron that produced that line, that color. So the process goes like this. When we put an atom in our flame test into the fire, the electrons, either the one electron or more likely all of the electrons in that atom, are going to get excited to a certain degree. To keep this simple, I'm just showing an electron getting excited from its ground state in the first energy level up to the sixth energy level. So the electron jumps up, it's in an excited state, but it's unstable. Just like everything else that goes up, it must come down. And there's a couple of different options for how it can come down. It's either coming straight back down from the sixth energy level to the first, or it could take it in pieces and go from the sixth to the second, and then to the first. But eventually, no matter how many different transitions it takes, it could go from the sixth to the fifth to the fourth to the third to the second to the first. But no matter what, it's gonna come all the way back down to that ground state. And that arrow going up is representing the amount of energy that that electron had to absorb in order to be excited and jump up to that sixth energy level. And those red arrows are all different variations as to how much energy could be released from our atom as light, so that we can see those differences in the energy levels inside our atom based on the energies of light coming out. And once again, I'm going to reinforce that these are very specific amounts of energy. If I gave an electron about 1.5 energy levels worth of energy, nothing would happen. It wouldn't jump up to the second energy level. It wouldn't jump up to the third. It wouldn't move at all because it doesn't have enough energy to get to an allowed place. So only the very specific amounts of energies could be absorbed, and that meant that only very specific energies of light would be released. We are never going to see something with the amount of energy between third and 1.5 level. It's just not allowed. So because we only saw specific types of energy or colors of light coming out of our atom, we knew that there was only certain energies of our electrons inside the atom. And we're about to put that down below where we wrote this, but I do want to point out that the longer these arrows are, these lines transitioning between these levels, the higher energy light that's coming out. That makes sense. I'd have to put more energy in to make it go up higher, and I'd get more energy out the longer, farther it falls. So this explanation that I kind of just said a moment ago is important to remember the difference between the continuous spectrum and the line spectrum, and why we don't see a continuous spectrum come out when we burn atoms. It's because of those electrons. This is what Mr. Bohr discovered about the arrangement of electrons, is that there have to be only certain specific energy levels for electrons, because they're what makes light, and we're only seeing certain energies of light. So there must be a limited number of energies allowed for our electrons. Now, let's get into some calculations. And I know it might seem like a lot, but all of the stuff on this page, out of all of it, the only real important part are our equations. So this wave equation, don't worry about why it's wave instead of particle. Light has a couple of different types of particles and kind of properties that it can behave in, but I'm never going to be asking you about those properties. Those are really more physicsy type things. Just FYI, we have some fun properties of light that we can play around with. What we need to be able to do is these calculations. So this first equation, c, this velocity or speed of our light, is a constant. It's always the same number, 3.00 times 10 to the 8th. Its units are meters per second. It is a speed, just like miles per hour. This is the speed of light, and it never changes. Even with all our different types of light, the energy, wavelength, and frequency change, but the speed does not. Then F stands for frequency, probably not too surprising. It does have some weird units though, just be on the lookout for Hz, hertz, or 1/seconds. Either way, that's technically what hertz stands for, Hz. Just need to be able to recognize that as a frequency number. And then this little upside down lambda is wavelength, and we measure that length of our waves just like the length of everything else in science, in meters. Now, if you're given nanometers, or if during the research for your lab you find some wavelengths that are given to you in nanometers, all we've got to do is add E-9 to the end of that number to turn it into meters, because that's what nano stands for. So, for example, 350 nanometers is equal to 350 E-9 meters. And that's something you can plug into your calculator, and I will show you how to do these fancy E's to make things work out better in our calculators with scientific notation. Technically, that just stands for the times 10 part of our number, and this isn't technically proper scientific notation because our decimal isn't in the right place. So your calculator will generally correct you to proper scientific notation and move that decimal, but you don't have to do that for your calculation to turn out right. But we'll work a lot more on the calculator side of things in class. We're going to have to rearrange this equation because the things that we might actually want to solve for, the frequency or wavelength of light, are not what this is set up to solve for. This equation is basically set up to solve for c, which is a number we're always going to have given to us. It's never going to change. So I'm going to rearrange this equation with the help of this triangle here into these two versions where I can actually calculate my frequency by taking that c number divided by wavelength, or find my wavelength by taking c divided by frequency. So in this first example on this page, we're going to do exactly that. I'm going to do a modified guess method here, find my given, which is the wavelength of light, big fancy scientific notation number, but that's still just my wavelength, and I'm looking for frequency. So if I know I have to have an equation with frequency and wavelength in it, and so far we just have the one equation, I still know that I want to rearrange that equation to solve for frequency because that's my unknown. That's what I'm solving for. And at this point, I just need to plug in my c, which remember is a constant. It's not in my problem, but it's always the same value, 3 times 10 to the 8th, and divide by that 4.90 times 10 to the negative 7th, and that will get me my answer. We're still going to be rounding things according to sig figs, and I know scientific notation is scary, but just make your answer match the numbers that you're given with the least number of sig figs. Just pay attention to the base part of things. The rest of that times 10 or e stuff is just a placeholder. So I just want to keep these first 3 digits, and so that is going to round to 6.12 times 10 to the 14th. And because this is a frequency I was solving for, I'm going to put hertz, Hz, as its units on the answer. Not too bad, I hope. Now, our second equation is down here underneath all of that particle behavior stuff, and this tells us that E, energy, which we are going to measure in joules. I know that you guys have seen that J before on our first test, and we didn't really understand what it was. It's just our units for energy. You already have the H written there, so you probably don't need to write it again. Just like our C, that is a constant. It's just a little bit of a different constant, 6.63 times 10 to the negative 34th. And JS, or joule seconds, are those units. And then F is frequency again, same units as always. So this equation is made to solve for energy, which is going to be useful to us, but we also might need to rearrange it to solve for frequency. So if I do that with the help of my triangle, my equation for frequency is energy divided by that H, which is Planck's constant. So let's do a couple of quick practice problems with that. Reading through this next example, it tells us that to find the energy of a wave with a frequency of this 6.32 times 10 to the 20th hertz. So if I'm finding energy, I need an equation for energy that has frequency in it, and that's the original form of this equation. So I literally just need to go and remember what that H stands for. It's a constant. We can always look it up, don't have to memorize it, and multiply it by that number I was given, and then we get our answer out, which we are going to round to 3 significant figures. And because this is energy, it's going to get joules as its unit. Last example here, as we start to analyze this, we're given wavelength, and it's asking us for energy. And this is where we're going to have a little bit of a problem, but it really is an opportunity in disguise. If we look at both of the equations that we've used so far, none of them have both energy and wavelength in them. So technically what I could do is use my green equation here to solve for my frequency, by plugging in my wavelength and my C, and then plug that into my frequency here in order to be able to solve my energy. But that's going to take a lot of time to do 2 separate calculations. So what I'm going to do here is combine these 2 equations together by solving for our frequency without any numbers in it. Frequency is just C divided by lambda. And then if I plug that in instead of the F in my energy equation, then I get this purple equation, which is going to be much more helpful here if I want to find energy and I'm given wavelength. So all I've got to do to solve this for my answer is plug those numbers in. I'd like you to try this out. I'm not sure whether your calculator is going to be able to handle the scientific notation, but do your best, try it out, plug in the numbers that we've got on this page for H and C, divide by this lambda number that you've got, and if we're doing everything correctly, we should end up with 4.71 times 10 to the negative 25th, and that will be joules. If you can't get your calculator to work right, at least try and set it up on paper, and I'll help you in class with how to put the numbers into the calculator to get everything to turn out correctly. So that's it. Last big idea in our packet. You got some practice problems that we'll work on, and we'll use this in our lab, and then we're done with Unit 2.